Hi friends, welcome back. In the last session we have seen how the critical system problem can be solved using a software solution. Now let's get into the hardware solution, and before getting into hardware solution, first thing is we need to know why the critical section problem arises. The critical section problem arises, as we have seen in the previous session, when the instructions of the multiple processes are interleaved while execution, and this will create inconsistency in the shared resources, and that's why we have a problem. So to ensure consistency of the resources, we must ensure that the critical section is run without any interruption. Now the reasons why there is a shift of execution from one process to other process, if we want to look at it, then we can see that it may be because of IO waiting. So one process is running, and it comes to a situation where it has to read the data from the IO, that is external devices, and as we have seen in the earlier stage, these external devices are quite slow compared to our system, and hence we don't want our process to keep running with doing nothing, because the process cannot continue till the information required from this IO reading is available. So it keeps waiting, and if instead of wasting the CPU's time, what we can do was we changed the state of the process to the waiting state. So a process which was in running state will encounter some situation where it needs to wait for the slow IO devices, and for that, instead of keeping the CPU wasting its time on this process, we can dump this process into a waiting list and say that till you get your data, you just keep waiting there. Once you get the data, then let's continue working with you. So that's one reason why the execution shifts from one process to other. Now what happens? One process, PI, was executing, and PI wanted to wait for some IO activity, therefore PI is jumped onto the waiting list. Then the next process, which is there in the ready list, that is the PJ, is shifted to the running state, and now PJ starts using the CPU and PJ starts running. So that's one reason why there is a shift from one process to other process. Or it may be like a round robin, each process is allotted some time, and once that time is out, then it will be forcibly stopped. That process execution is forcibly stopped, and another process is given chance to run. So when a process times out, then it is stopped, and that process changed from running to ready state and put it onto the ready queue. Then the other one, which is supposed to execute next, will given a chance. So that is taken from the ready queue, and its state from ready changed to running, and it starts using the CPU. In the third case, one process, maybe a low priority process, is running, and while it is running, a high priority process comes and asks for the CPU's time. Then the low priority process is forced to stop, and then the chance is given to the high priority process. So There are mainly the common reasons for shifting the execution from one process to another process, that is allocation of the CPU from one process to other process is shifted for these common three reasons. Now actually how it is done, when you know that it is waiting, what we should do, and when we know that it is scheduled timeout, what we should do, and when we know that a high priority process comes in, what we should do. So there are some actions to be taken by the operating system, that is the process manager has to ensure some activity so that the correct procedure is followed, and that is done through a signal called an interrupt. That's at the hardware level. We have something called a signal, and that tells or it stops the execution of the any process which is currently processing, and that interrupt is fed in, and the processor understands that something different has to be done, so it stops its current execution and looks for what is required. So there are different reasons for stopping one process and continuing some other process. So one reason, IO waiting. Then IO waiting will give some type of signal to the processor to interrupt it, and says that this current process we cannot continue because it wants to wait for some IO operation to happen. Therefore the process changes its state from running to waiting for the block state, and then next in the ready queue gets a chance to run. If it is a scheduling timeout, then we run a scheduling code that identifies who is next in the queue, and that next process will be given another time slot to run. Or if it is a high priority process, then it has its own way of working, so the process gets in and all that. So everything, whatever happens, one thing is common, is whenever we want to shift process from running to non-running state, it may be waiting state, block state, or ready state, whatever the reason is. Yes, for shifting we have to stop the process where and when we want it, and for that we make use of something called an interrupt. Now back to our problem, that is the CS problem, which says that whole set of instructions have to be run either totally or nothing. So that's a critical section problem we are talking of. So when one process is running its critical section, some part of the critical section is run, and during that some interrupt occurs, then it has to stop there and attends another process. So that's a tragedy we face. Yeah, interrupts are meant for some purposes, but in this case, when we are working on shared resources, the same interrupt is creating a nuisance to us, and to ensure that such nuisance is not created, then yeah, at hardware level we do have some process called masking. So we can mask interrupts, say that till I tell I don't want to be interrupted. Till I tell I don't want to be interrupted, it's like shutting down our mobile phone, or keeping our mobile phone in silent mode, or in aeroplane mode. So here I am the authority. When I want, I start it, and when I don't want, I again open it. So this masking is under the user's control, or the processor's control, or the operating system's control. If we can make use of this, then yes, that can be achieved. So what we can do is, before entering a critical section, make sure to mask all the interrupts so that none of other processes can interrupt the current process, whatever be the reason. And once our critical section problem is solved, then we can just release the interrupts and unmask the interrupts so that other processes are now free to interrupt. So this way we can ensure to have undisturbed critical section execution. This is possible when we have a single processor and shared resources, multiple processes. Single processor, multiple processes, and shared resources. Yeah, that can be controlled through masking the interrupts. But what if we have multiple processes and multiple processors? Each process may be connected to a different processor, and now each processor will have its own interrupt and all that. So one processor cannot control the interrupt of another processor and all that. So that becomes a clumsy thing. So in that case, what we can have is a special thing which we call lock. So we need something like a lock which works at the hardware level, number one, and number two, that the log is another part of the set of instructions, but only difference is when these set of instructions are being run at the hardware level, then all the set will be either completely run or none of them is run. That means atomicity is maintained by the hardware, not by the software, but by the hardware. The hardware, the processor itself is designed such that some special features are given, which we call a log, and this log will, when we are working with the log, then the operations whatever we are performing are in atomic in nature, and that makes things easier. So log is a synchronization mechanism used to enforce mutual exclusion. Yes, that's what we just discussed, and this ensures that only one thread or one process can be working on the critical section, not more than one. Anytime maximum one process or one thread can use the shared resource at any given time. So that's what a mutual exclusion is, that's what a critical section is meant for. And this avoids the race conditions, and we must get the log before entering into the critical section. So what we can do is we announce that we want the log. If I get a log, then I use the critical section, and once I use critical section, I unlock it. But who will give me the log? The hardware. The hardware has got a provision of this, what we call a lock. How it is implemented? Yeah, there are different ways of implementation, but yes, lock is a special hardware level instruction that is running in atomic way. That means either that whole instruction is completely executed or nothing is executed, either full or none. So that is atomic execution, and So the lock is released once we come out of the critical section. So in case of uniprocessor environment, just we discussed earlier, we just mask the interrupts from occurring while a shared variable is being modified. Yeah, when a shared variable is being used, so ensure to mask all the interrupts, and that is possible when we are working with a uniprocessor system, single processor, multiple processes. Yes, one of the processes can be allowed to use shared memory, then I can simply mask all the interrupts. When one process is given a chance to use the shared resources, we forcibly mask all the interrupts and then allow one process to get into a critical section, and the moment that process comes out of critical section, the interrupts are unmasked. So that's the simplest way of taking care of when we are working on uniprocessor, but that is not true when we are working on multiprocessor. So when it is multiprocessor, then we need some more detailed way of solving this. So the same lock mechanism, whatever we are talking, we have multiple locking mechanisms to take care, and then let us see how they can be implemented in the coming sessions. So till then, take care. Thank you. Bye.